in this unit, we're going to be mainly using exponential functions. So we've seen quadratics, we've seen linear functions, we've seen the radical functions right before we went on break. And we're going to get into exponential functions now. Now, exponential functions are when the exponent is a variable. So your variable is in your exponent. We're going to be specifically looking at this constant rate of change exponential function, where your base, so your base number is the number that's being raised to the exponent. It's always 1 plus r or 1 minus r. So it's always 1 point something or something less than 1. And r is the constant percent rate of change. I think that's a blank on your paper. So it's how much our equation is changing by some percentage. All right, so we're going to look at these two equations to prove they have the same percent rate of change, so the same r value. So they give us y equals 1.33 to the x and 0.67 to the x. So we're going to take both of these and we want to prove that they have the same r. So for all of these, we're always going to think of 1 plus what will get me to that base number. So in this case, our base number is 1.33. So we want to think of 1 plus what number would get me to 0.33. What number is it?
0.33.
Yeah, 0.33. So we have to add 0.33 to get to 1.33. And then for the second one, we want to think of 1. Now, if we're less than 1, we're going to be subtracting a number. We want to think of what number do I need to subtract from 1 to get to 0.67, which is also 0.33. So they have the same r value, it's just one time we're adding it, so we're increasing by a certain rate. And then the other one, we're subtracting away that 0.33, so we're decreasing by that rate. All right, so just to complete these statements, I don't think there's a blank right here on your paper per percentage, so just write it where you can. But for the first one, we said that our equation 1.33, we said that it was 1 plus 0.33, so we're adding the 0.33, so that's going to be an increase. So whenever we're adding our constant rate, it's an increase. And then we always want to write our final answers in a percentage. So if r is 0.33, how do I change a decimal into a percent?
You move the decimal over 2 to the right.
Yeah, you can move the decimal over 2 to the right. That's the same thing as multiplying by 100. So 0.33 written as a percent is 33%. So if we're adding our r, it's going to be an increase. For the second one, we were subtracting the 0.33, so that's going to be a decrease, and it's the same 0.33, so it's going to be, we're decreasing by 33%. So for this first one, we're going to just start looking at this, and then we're going to apply it to our actual real world scenarios. So they give us some equation, y equals a 16 to the x over 2. We're going to rewrite our equation first to get our actual base. So right now, 16 is being raised to the x over 2, and we want to split it up because we want to get our variable by itself when we're looking at these equations. And when we raise an exponent to another exponent, we're multiplying. So we want to think x over 2 is x times what? What's the same as dividing by 2? Multiplying by 1/2. So we're going to split up this x into x times 1/2. So we're taking 16 to the 1/2 power. And on your paper, I think part B says rewrite the base to reveal the percent rate of change. It should say reveal the growth factor. So we're not looking for the rate of change yet. We're looking for the growth factor. Your growth factor is just whatever the base number is. So whatever number we're raising to the exponent. So we don't want to write it as 16 to the 1/2. We actually want to take 16 to the 1/2 power. So this is where we need our calculators. So you want to do 16, raise it to the 1/2 into your calculator. And someone tell me what they get when they plug it in. 4. Okay. So 4 is your growth factor. It's how much our equation is growing. Yeah, I know. So one more time, I think your paper says rate of change, but it's just a growth factor for part B. Part C, that's when we're going to find the rate of change. So your percent rate of change, that's your R value. So this is where we want to think of 1 plus what would get me to 4. It's like this is our base right here. So what would I have to add to 1 to get to 4? 3. So R is 3. And we want to write it as a percentage. So what is 3 written as a percentage? 300. We're going to multiply by 100. And for all of these answers, we're going to write like it as like a sentence. So for adding, that's an increase. So for this one, it's a 300% increase. Yeah, Brandon.
Do everything to the x at the end. Is there a reason for that?
Like right here?
Yeah, like above the 3. Put that x up there.
Like right here?
Yeah.
Yeah, I was just like rewriting this. I'm rewriting the whole equation. I just didn't write the y equals in the a in the front. So like I was just thinking like I was rewriting this part right here. So I wrote the x. Other questions? Okay. All right, next one. So the next one we're going to do the same thing. We're going to like split up our exponents, figure out what our base is. I think this is another typo on your paper. So part B, we're finding the growth rate, not percent rate of change. So we want to rewrite our base because right now I have 4/5 raised to the 3x, and we want to get the variable by itself. We only want the x. So when we raise a fraction to an exponent, we have to raise the top of the fraction to the 3rd power and the bottom of the fraction to the 3rd power. So we have to do 4 to the 3rd power and 5 to the 3rd power. So if we change this, it would be 500 times 4 cubed is 64, 5 cubed is 125. And we're going to write this for like to figure out what our base is as a decimal. Round your decimal to the nearest thousandth. So that's 3 places. So do 64 divided by 125 should be 0.512. So this 0.512, that's your growth rate. And so now we want to figure out what R is. So we want to think about 1, and this one's less than 1, so we are subtracting this time. Would get us to 0.512. Should be 0.488. So that's our R. So our R is 0.488. But we're going to write it as a percentage. How would I write that as a percent? 48.8. So for our answer, we are decreasing by 48.8%. Because this time we're subtracting, so we are not increasing, we're decreasing. All right, so now we're actually going to apply this to some real-world examples. So for our first one, it says data from the U.S. Census released in May 2020 listed Flagler County, Florida as one of the 100 fastest growing counties in the nation over the previous decade. The function f of x equals 95,692, 1.202 raised to the x over 9 can be used to approximate the population in Flagler County, where x is the number of years since 2010. So we're going to use our property of exponents to rewrite and figure out what our growth factor is. So that's where we need to split up our exponent. So we're going to take our function, so the f of x equals 95,692, 1.202. And we want to raise it just to the x power, so we need to split this x over 9 into x times something. What do I need to multiply by? What do I multiply x by to get to x over 9? 1/9. So we're going to take that 1.202 and raise it to the 1/9. If you need help plugging into your calculator, let me know. I'll help you. Round your answer to the nearest thousandth. Someone tell me what they get when they get it. What'd you say, Cushy? 0.134. I might have to help you because that's not right. Alright, so you should have gotten 1.021 raised to the x. So that 1.021, that's our growth factor. So your growth factor is your base. R is when we try to figure out 1 plus what would get to the 1.021. So it should be 0.021. That would be our R. Which would be what as a percentage? 2.1. And so for our answer, though, we're going to write it as a sentence. We're going to write it in the context of this problem. So looking back at like the original problem, it's talking about the population in Flagler County in the number of years since 2010. So our population, is it increasing or decreasing? It's increasing. Why? Because we're adding. So our population is increasing by 2.1%. So something along those lines, you can say population in Flagler County, doesn't really matter, just something along the lines of the population is increasing by 2.1%. I'm mainly looking for that you know like what it's talking about like in terms of population, if it's increasing or decreasing, and then you got the right like percentage. Alright, so our next one is about Crusoe. He's a dog. He's known for his adorable videos on social media. The relationship between the number of days D and a post with his brother Oakley and his sister Daphne and the number of views they get on social media is modeled by our function. This should be V of D. V of D equals 1,568 1.17 raised to the D. So D is the number of days. So right now we can go ahead and we see our growth factor. There's nothing in the exponent that we need to split up. What's our growth factor for this one? 1.17. So we're growing by a factor of 1.17. So we want to find the constant percent rate of change. So we want to think 1 plus what would get me to 1.17, which would be 0.17. How do I write 0.17 as a percent? 17%. And is that a 17% increase or decrease? Increase, because we're adding. So our constant percent rate of change per day will be a 17% increase. So his views are increasing by a lot each day. All right, so the second part wants us to figure out what are the views per week. So we're going to rewrite our base and figure out our new growth factor and figure out our new rate of change. So W is the number of weeks for the new function. So we need to replace D with W. But how many days are in a week? 7. So we need to put not just W, we need to put 7 W. So you want to think of like there's 7 days per that week to get the amount of days. So we're going to be raising this to the 7W instead of just D. So if we split up our exponent, we want just the w on the outside, so we're going to be raising this 1.17 to the 7th power. So if you do 1.17 raised to the 7th, you get like 3.001. So we're just going to say it's like 3. So what's our new growth factor? What's our new base number? What do we get? What's our new growth factor? New base number for this one. Per week. 3. So if we want to figure out our constant percent rate of change, we want to think of 1 plus what would get me to the 3. What do I need to add to 1 to get to 3? 2. So our R is 2. How do I write 2 as a percentage? 200%. Yeah, Reagan, or Reese. I don't know why I called you that. 3 is the growth factor because it's the new base number. 1.17 to the 7th power. What? No, I did 1.17 to the 7th power in my calculator, like you should be doing too. Alright, so we're increasing because we're adding, we're bigger than 1, so we're increasing by 200%. So in this problem, we're talking about the number of views, like on his videos. So for your answer, you need to say something along the lines of like, his number of views is increasing by 200% per week. Alright, I want you to do the next one. So top one on the back of your paper. Alright, so if we want to start rewriting this, so we got 2,550, 1.85. We want to just raise it to the t. What's going to be my exponent that I need to raise 1.85 to? It's a fraction. 1/10. Yeah, we want to split that t up into 1/10 times t. So what's my new base gonna be? Right here. It's my new base. When you plug that in. 1.063. So that 1.063 is our new growth factor. So then we want to find the constant percent rate of change. So we need to figure out what R is and like interpret it in this problem. So we want to think 1 plus what would get me to 1.063, which would be 0.063. So your R, if you write that as a percentage, is 6.3%. Okay, so from this problem, someone raised their hand and tell me, like, what's the sentence they wrote for your interpretation? What did we, was increasing? Cost of what?
Annual function.
The cost to go to college. So this problem is talking about the average annual cost. So the cost to go to college is increasing because we're adding the 6.3% each year. We're talking about years. So something along the lines of the cost to go to college is increasing by 6.3% per year. All right, so for this one, we're talking about the honeybee population. It was steadily declining due to a phenomenon that researchers have named colony collapse disorder. Honeybees are vital to crop pollinators, so Florida began the process of educating its citizens about the importance of bees to help save the bee population. From 2006 to 2013, Florida saw unprecedented growth in its honeybee colonies. The growth could be modeled by the function B of x equals 150 1.129 raised to the x, where B of x is the number of honeybee colonies in thousands x years from 2006. So x is the amount of years since 2006, and they want us to rewrite it so it reveals our monthly growth rate. So we want to change this to a monthly growth rate instead of a yearly growth rate. So we're going to take this 150, 1.129, so we want to take that year, but we want to just look at the monthly growth rate. So how many months are in a year? 12. So we need to take x, so whatever year, and divide it by the 12 months in the year. So we want to look at just 1 month out of that entire year. So we're going to replace this with x over 12. Right, we're getting smaller with our growth rate because we want to take our whole year and like divide it by the different monthly rates. So we need to find our new base number. So we need to do 150, 1.129, and we want just x. So we want to split this x over 12 into x times something. What's my fraction going to be? 112. So we're going to raise that 1.129 to the 1/12th in your calculator. Someone tell me what they get. Round to the nearest thousandth place. Grayson. 1.01. Okay, so if there's another 0 on the end with the decimal, we technically don't need it, so we're just going to write 1.01. But that is right. So our monthly growth rate is the 1.01. All right, so now we want to figure out what R is for our last part. So 1 plus what gets me to 1.01? 0.1. So if we change that to a percentage, what's 0.01 as a percent? 1%. So in this problem, we're talking about the number of honeybee colonies. So are they increasing or decreasing per month? Increasing because we're adding. So we need something along the lines of the number of honeybee colonies is increasing by 1% each month. Say monthly, each month, doesn't matter. We're going to briefly talk about this one. It's kind of small on the screen, but a population of cicadas in an experiment is modeled by this function. W is the number of weeks. We want to find the constant % rate of change per day. So we need to figure out what our new growth rate is and then figure out what our R is. So we want to take this 7,000, 1.2. So we're taking a week and we want to split it up into each day. How many days are in a week? 7. So we want to take that week, W, and divide it by 7. So we want to look at just one day out of the week. So if we split this up, this will be 1.2. What's my fraction going to be that I'm raising 1.2 to? 1/7. So do 1.2 to the 1/7 in your calculator. What do we get? Round to the nearest thousandths. 3 places. To get 1.03, rounded to the nearest thousandths place. So give me 3 decimal places. 0.026. Okay. What are they asking us for? Rate of change. So we need R. So we need to think 1 plus what would get me to 0.026, which would be 0.026. So 0.026 written as a percentage would be 2.6%. Sorry, R. And are they increasing or decreasing? You said increase. So they're increasing per day.